All right, here's the warm-up answers. I showed a lot of work here. You clearly don't have to show this much work. Again, and if you didn't get the exact 384, it's probably just because of rounding. Here's your homework answers. You can pause this video if it's going too fast. And here's the lesson. So basically what we have to do is we have to do the same thing for means that we did for proportions. So what we start off by using an easy transition here. So we start off by estimating the population mean when sigma is known. So everything kind of looks here the same with these 4 steps. We got our state, our plan. Now what happens here in our plan is that you'll notice it says one sample z interval for means. So that's different than what we had before. The random check still the same. The normal check is now different. So since we're talking about means, either the population is going to be normal or the sample size is going to be greater than or equal to 30, which is that central limit theorem. The independent check, we're still with our 10%. All right, there's 2 options here. So here's the formula. The formula, it's always still the statistic or the point estimate. In this case, the statistic is x bar, plus or minus. We're still using z star, so it's the same critical values. And this is your standard deviation, the statistic. Since we're talking about means, it's sigma over the square root of n. There's an option here to use the calculator as well, and then you just do your interpretation. So here's the president of a university wishes to estimate the average age of all students presently enrolled. So I know this isn't a proportion right here because it says the average age. He takes a random sample of 50 students. He finds the average age to be 23.2, so that's the x bar. And it says, suppose that it's known the standard deviation of all the ages of all students at the university is known to be 2 years. So that's telling me the population standard deviation is 2. Calculate the 90% confidence interval. Here's step 1. This right here, all of this is my step 2. So I'm saying I'm doing a 1 sample z interval for means. It says he took a random sample. The normal check here, it's the sample size is greater than 30, greater than or equal to 30, so the central limit applies. I'm going to assume there's at least 500 students. If I wanted to do the formula, there's my x bar. It's 90%. The critical value is 1.645. And then you're going to do just the standard deviation, so 2 over the square root of the sample size. There's the answer. If you want to use the calculator, there's the inputs. There's the answer from that. And then we write that statement the same way we've been writing the statement. Sometimes we can find the minimum sample size for these ones. It's the same idea as it was yesterday, but obviously the standard deviation formula is different. We have sigma over the square root of n. You're still solving for n. You still round up. So here we want to estimate the mean IQ score for the population of statistics teachers. So it's asking us how many, so we know we're looking for a sample size. Teachers must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 2 IQ points. Now these aren't percentage points. They're just actually 2 points here. So 95% is my 1.96. It tells me to assume a sigma is 15. I'm looking for n, and the margin of error is 2. So I'm just plugging that in, solving this. I'm going to round up just like I did before. Okay? All right, now this is all wonderful, lovely. The problem is it's not very realistic because the reality of it is if you were trying to estimate the population mean, you probably don't know the population standard deviation. I mean, most likely you're not going to know either of those things. So what happens is that instead of using the z distribution, which is what we're familiar with, we actually use the t distribution. So we're using the t distribution in the situations in which we're using the sample standard deviation, sometimes I call that SX, to estimate the population standard deviation. So basically, the story goes like this. So there was this guy. His name was William Seeley Gossett. And he was working for, he had a degree in chemistry and math, I guess. And he was working for Guinness. He went to go get a job at Guinness at their brewery. And he was doing some research. And he was looking at small samples. So he was looking at samples of about size 4 and using the sample standard deviation and the sample mean. And he was standardizing those values. Now, when I mean standardizing, what I mean is taking like a formula like this. So you're familiar with that standard score. So we have z is equal to the mean minus we have the value minus the mean of the standard deviation. So in this case, he's taking a sample of size 4, he's finding the sample mean, and he's subtracting what he believes is the population mean, and dividing it, he's using the sample standard deviation over the square root of his sample size. In that case, it's 4. And what he's finding is that he's having way too many values out here, because he says if this is truly a normal distribution, when I standardize these scores, I shouldn't see a lot of z-scores that are -3, -4, -5, or likewise I shouldn't see 3 over here, 6 or 8 or even 10. Like, he's just seeing these values way more often than he would expect. And that leads him to study it a little bit further and decide that, hey, if you're using the sample standard deviation instead of the population standard deviation, we're no longer following that z distribution. This is a new shape. I'm going to call this the t-distribution. How he came up with such an original name, I am not sure. But anyways, and then there's some stories here. There's conflicting information about if he actually was able to publish it, because if Guinness restricted his publication or not. And I've heard different stories about what the actual truth is. But sometimes it's called, he did publish it regardless under a pseudonym named Student. And so sometimes it's called the student t-distribution, versus just called the regular t-distribution. So the student t-distribution, like I said, sometimes it's called that. So what happens with this t-distribution, what he also found out is that depending on your sample size, that shape is a little bit different. Now in stats, what we do is when there's a distribution that has different shapes based on the sample size, what we usually do is we define something called the degrees of freedom. So the degrees of freedom is just n minus 1, so the sample size minus 1. You might be asking yourself, why don't we just use the sample size? If we only had the t-distribution to worry about in stats, yes, maybe we could use the sample size, but there's many other distributions that we're going to use, and the degrees of freedom will change. So that's why we just kind of stick with degrees of freedom instead of sample size. So the degrees of freedom are just n minus 1. All you need to worry about as far as the degrees of freedom are concerned is, 1, remember that it's n minus 1 for this particular test, and remember that the degrees of freedom are important when a distribution has a family of curves. So here's a picture here. The standard normal curve is this blue curve right here. When I have a degrees of freedom of 1, you can see this is your t-distribution. It's still bell-shaped, it's still centered at 0, but you can see that there's a lot more area here at the tail. If I increase the degrees of freedom to 2, you can see it got a little bit taller, less area in the tails. Remember, the area under the curve is still 1. As I keep increasing that degrees of freedom, this t-distribution approaches that normal distribution. So it ends up essentially becoming almost the same curve. The critical values might be a little bit different, but it's essentially almost the same curve. But what is important to note here is that if you wanted to get a 95% confidence interval and you only have a degrees of freedom of 1, and I'm using this green curve right here, in order for me to capture 95% in the middle, I'm going to have to go further out than I had to go in that blue curve. So my critical values are going to be different now. All right, how's the t-distribution similar? Like I said, there's still a mean at 0, and they're both still bell-shaped. How it's different, the t-distribution is not just one curve. There's multiple curves. We say a family of curves. And the spread is definitely greater, or there's more area in the tails, okay? All right, so since we now have this new distribution, we have to find critical values differently. The idea is the same here, so you're still trying to capture that middle area. So if you wanted to do a 95% confidence interval, you had a sample size of 12, the degrees of freedom would be 11. So there's a chart that you could use, and you can look up the degrees of freedom And then if you look at the top of the chart, it says tail probability. If you look at the bottom of the chart, it says confidence level. So you see 95%. So I would go 95%, and then I'd find the degrees of freedom of 11, and I'd see where that row and column overlapped, and I'd get this number right here, that 2.201. So that tells me that's my critical value. Likewise here, 95% in the middle, it's sample size of 25, degrees of freedom of 24. I'm going to go here in this table, 24, 95. I'm going to see where those overlap. There's that 2.064. And then I can do the same thing for the 99. What you'll notice here is that, or what you'll see about the table, there's limitations to the table. Once we get up to like 30, we start jumping up by tens in the degrees of freedom. So the table doesn't have every possible degree of freedom. The table stops at it gets to a certain point. And also what happens with the tables here is you can see these last values. So if you look here at the 90%, the 1.645, 95 is 1.96, the 99 is 2.576. So what you'll notice there, basically the t-distribution is converging to that standard normal distribution. So the table just kind of makes it short like that. There's a calculator option. So instead of using inverse norm, you use inverse t. It works the same way as inverse norm with the exception that we have to add the degree of freedom. So if I was doing a 95% confidence interval, the area to the left over here is 0.025. So I could do inverse t 0.025, comma the degrees of freedom. Or in this side right here, the area to the left of this one is the 0.95 plus the 0.025. And I get that 0.975. And so then I can get that answers. The calculator is sometimes a little bit easier to use just because it doesn't have the restrictions of the length of the table. All right, so what looks a little bit different here? So now we're estimating it, we don't have sigma, we have the population, we have the sample standard deviation. The inference method, it's a one sample t interval for mean, so I'm not using z, I'm using t. Random check's the same. The normal check, the idea is the same here. There's one exception here. The t-distribution is considered robust. So there's times when this condition is not. So at times, since the normal condition might not be met, but the t-distribution is considered robust, so oftentimes we can still proceed with the procedure and be okay. Like our results will still be pretty accurate. And then we have our familiar independent check. Here's the formula. If you notice what's different from the first page is we have this t star instead of z star, and we have s or sx instead of sigma. And then there's an option on the calculator. Interpretation is the same. Standard error of the mean, so the standard error of the mean, we're just plugging in S instead of sigma. Again, the same idea, you're plugging in the sample value. So like previously we were plugging in p hat instead of using p. Now I'm plugging in the sample standard deviation instead of using the population standard deviation. So I have this example right here. So they're claiming students spend at least 10 hours per week doing homework on average. So they're going to select a random sample of 250 students and ask them how long they spent doing homework the last week. So this is the sample mean, and the sample standard deviation is 4.2. So I know I'm estimating the mean, and they didn't give me the population standard deviation. They gave me the sample standard deviation, and I want to find a 95% confidence interval. First statement's the same. This one looks familiar. This is familiar. We're greater than or equal to 30, central limit theorem applies. I'm assuming that there's this many students at a large high school. Hopefully it's like a North Allegheny large high school. All right, if I'm using the formula, if I'm doing 95%, I need to find a new critical value. So you could do 0.025 would be in the left tail, or the upper boundary would have 0.975 to the right of it, or to the left of it, sorry. The degrees of freedom is the sample size minus 1. I get that critical value. X bar, the t star, s, square root of n. I get that interval. You can use the calculator option, plug in all those pieces, get the interval. This last statement here looks pretty much the same. The last problem here, it just says that, so sometimes with that normal condition, I'll spend a little bit more on this on the next lesson. So what if the sample size is small and we don't know the shape of the population? So if we can look at a graph, and as long as we don't see any major skew or outliers, we can usually proceed. So here's an example. Here's some data here. Now in this one here, you're trying to find a 99% confidence interval for the true mean number of squares of toilet paper that it takes to absorb this much water. So I know I'm doing, and they don't give me the population standard deviation, so I have to use T. The random, it says they did a, they randomly selected. What I did is I put all that data into a list, and I looked at the histogram. You could look at a box plot if you wanted, or the normal probability plot. There's clearly at least this many rolls of toilet paper. At this point here, what I did is I used the calculator. When you go into the calculator, when you go to that stat test, you go to option 8. You'll see at the top there's two options there. There's a data option for the input and there's a stat option for the input. You can use the data option. If you use the data option, then you just have to put the list name in for list, leave the frequency as 1, put your confidence level in there, and then just hit calculate. If you want to use the stat option, you're going to have to calculate the X bar, the SX, and the N. So you're going to have to use like 1 bar stats or something to find those. Regardless, if you're using the calculator, I still need to see these pieces here, and I need to see the answer. If you're using the formula, you're going to show me that anyways because it's all in the formula. And then you're going to write that summary statement there. And that is it.